lava flows, and then two-phase flow in pipes. A few topics today to describe eruptions. So lava flows has been one of the first things that people have tried to model, because it is relatively easy if you want to do it. It's not that easy, but it's relatively easy to find simplified models that work for lava flows. We will have a look a little bit at what is available. And also because it has an impact, a direct impact on people, and also because it is a phenomenon that occurred at the first volcanoes that had a volcano observatory. Like the very first observatory was at Vesuvius, and then in Hawaii there is an old one, and then Etna, and all these volcanoes have very strong effusive activity. They can also have explosive activity, but a lot of people already in early times, they studied lava flows. So there are approaches. Approaches are divided into two types or three types. One is like purely statistical, like you don't put any physics in them. You just go to the volcano and look where previous lava flows were, and then you assess the probability that a new flow will cover that area only based on the previous probability. No physics at all. Then there are fully physical models which describe really the rheology of the magma and the flow in terms of differential equation, with variation of viscosity depending on the magma, depending on where on the flow it is, if it is at the edge. And so you have a vertical profile in the lava flow, and you have also a downstream profile in the lava flow of viscosity, and depending on this viscosity function, then the flow proceeds. And then of course you have topography, the slope. And then there are models which are a little bit in between. So they strongly simplify the physics, but they keep the main point, probably, or at least in many cases it's the main point, which is the slope, gravity. And they simplify the rest, and they only consider the where, how the steepest path, so basically where the flow would go, and they have like streamlines for this flow. Of course, if you do this, it's more like a probabilistic thing, because you need to, so if you only do the steepest path, it's going to be only just one trajectory for every point, because it will be individual streams. And so basically to counterbalance the fact that it is a bit too strict, what they do, they add a probabilistic part where they jump a little bit here and there to account for smaller variations in the topography that you cannot have in a model, like very tiny, bumps and things. And in this way, just to basically jumping a little bit on this path, they are able to construct a lava flow. So actually there are many models. They work in different situations, and as far as I know, they have not even been compared very well. So I cannot really show you, like a situation, like a true comparison, like with a lava flow at whatever volcano, or even at more volcanoes, and people using different models and checking what are the conditions to use one model and what are the conditions to use the other model. As far as I know, there is no such comparison. So, and the reason is that people should be working together to do this, because everyone has this code and they use it, and they maybe compare with previous results of other people, but it's not really a proper comparison, because you would need to collect in a team or everyone and say, okay, now you run it, and then in the end we compare. And these things are still rare. It's a pity, because it would be interesting to check. Anyway, so basically the important factors are listed based on the statistics, or anyway data are important just to collect the data and have a maps of previous lava flows. Some people just use that. Then you have an important factor, which is the spatial distributions of the vents. We will see some examples. The problem is when you have a volcano where not all eruptions occur on the summit, but they occur from fissures that open on the flank, then you cannot have a lava flow model without having a statistical or physical model for where the vent is going to happen, because of course this is a critical input. So where is going the lava flow start? And then what people do is to manage this vent map, you know, like it's like an input but very uncertain. Anyway, where is going to be the eruption actually, when it's going to be, where is going to occur. Then you also have there is a timing component, so how often do you have an eruption on that specific volcano. Then you have the topography model, which is very important, and then you need to have a rheological model of magma if you really want to have one fully physical model, where the chemistry of the magma and the physical properties are coded into a model that describes especially the variation of viscosity as a function of temperature. Okay, these are like the very early lava flow models. As I said, they are based on previous maps, so the very first preliminary work is really for geologists to go to the field and map these flows, date them, you know, like take samples, date the flows, map them, and then you have maps like this. Of course, there are uncertainties because newer flows cover previous flows. So completeness of data is tricky because you only see really well those that are more rare actually, and you see less well those that are more frequent because they cover each other, while those that are more rare, they occur lower on the flank. Like for Etna here, you see this one that covered Catania, and then there are other ones. These were all originated from fissures that were like halfway from the summit to the coast, and these are quite you know, well mapped, but of course a lot of the flows that occur here, you don't know them. So your statistics is a bit tricky too. These are a vent map for or actually more than a vent map, is like a map where you have, yeah, it's like a density map for vents. So it's very rough, it's not really, all vent maps are really very rough, generally they are coarse. You don't have a very smooth, or if they are smooth, they are artificially smooth, because actually we don't know. What we know is, okay, there are, you know, all these dots are previous cones and vents of previous eruptions, and then you know, what people can do is to assign a very high probability where you have really dense vents, you know, close to the summit, and then you say very high vent density, then you say intermediate vent density, like here in this case. Here they say more than one vent per square kilometer, here from 0.5 to 1 vent per square kilometer, and then you get the gray area. And then where the Etna volcanics are, which is the whole thing, so you can assign a probability 0, so it's really, you know, you have to do an exercise of guessing, which is very hard. You cannot really very much base it on the physics yet. It's really like a guess exercise of where these vents are going to be, at least so far. Yes, and then from such a map, you run your model. If you want to have, you can have, another point is all hazard models, like lava flow or pyroclastic flow less, but lava flow certainly, you can run them when you are in peace, like nothing is occurring at the volcano, you just want to know, you know, it's like a long-term forecast for lava flows. And then what you do, you take such a map and you think, what is the probability that an eruption occurs at particular vents? Like also, you know, one thing is the density, but one thing is also the probability. What is the, you can say one eruption for each vent, or you can say, no, actually my probability is higher, you know, it's a function of elevation. More eruptions occur at higher elevations, less eruptions occur later on. So you really need to know the history of the volcano to actually do these guesses, because there is no rule yet. There is no, every person has a different approach. It's not codified yet how you actually tackle this problem very well. So then you have the map, and then you can say, okay, I run like one model from each vent. And then there is another problem, which is how much mass will actually erupt from that vent. You know, because will the flow stop early on, or will the flow be very large and not stop until it's really long? And then you can again there do like a statistical analysis, and your statistical analysis can be global for the volcano. How many flows reached what length, for example, in the past? But then you can say, okay, I can look also at an elevation statistics, like are they maybe the lower flank, are they longer in comparison if we go back? At some volcanoes it has been found that actually the lower flank are generally larger. It may be true also physically, because if you connect a pressure source through a conduit to a fissure, you know, at the dike intersects with the surface, it creates a fissure, and then from that point in time, a flow will start. It may be that, you know, the same pressure at the same magma chamber, if it needs to send the magma to a very high elevation, or if it just goes laterally, it's easier, you know. And so the pressure balance in the end will help to drain the chamber more. Some people say, so like I've seen at least one publication from on Piton de la Fournaise in La Réunion, which says exactly this. But this is very, very new work, so that people try to actually find the statistics to inform the hazard models. Okay, so, you know, it's like if you want to have a long-term map, you need to consider all these things, assign a probability from every vent, run your models, assign a probability for the total mass that will be erupted, and then or a length of the flow when you stop your simulation, and then you can do, and you get as a result a lava flow map. Like these were very early lava flow maps. This is a newer one, 2013, where they used, you know, similar approach to create this probability of inundation. And then if you, what I don't think has actually been done at all, in theory you should also take these maps and wait a few years and see how well maybe different maps are performing, because you know, a test for this kind of forecasts would be necessary. Like, what you can do is also you use, you know, like for Etna or Piton de la Fournaise, these are volcanoes that erupt frequently. So you can say, I'm going to use the data only until 2000, available until 2000, on which I will base my flow model, and then I will use the eruptions from 2000 to now to actually test the model, for example. And but this is not really done very much. So there are a lot of things that needs to be done that have not yet been done. This is an example from Fogo Volcano. I know better this example because it was done by a student in my department, and so I didn't contribute to the work, but I followed her and I helped her a little bit, so I know better this case. So this is Fogo Volcano. in Cabo Verde. It is off the coast of West Africa, a little bit in the middle of the ocean actually. It is a volcano. If you look at the shape of the volcano, it has a very big collapse scar here. And most eruptions have occurred within this area, which is called the Chada da Caldera. Some eruptions have also occurred outside. And here are indicated like 3 towns, but I think there are more towns, not only these 3 or 4 that are indicated here. The topography is very, you know, extreme. Like you have like a scarp that is very, very high here, like 1 kilometer scarp. And this is the whole archipelago. This Pico de Fogo here is this cone here. And it is where actually close to which most eruptions are currently occurring. In particular, this is a lava flow that occurred in 2014-2015 from a vent that was located more or less here. All the flow came in like this. It was a very large lava flow, quite large, like I think 20 meters thickness, so enough to cover everything on a path. You see a bit better here the geometry, like here is the vent that opened on the flank of this Pico de Fogo, and then the lava flow. And you see that the lava flow covered part of this little town or village and this other village here. The reason why people live there, even if the flows have occurred there in the most recent past, is that it is a better climate. It is a very mild climate up there, and the soil is fertile, so people still want to live there, even if it is more dangerous than on the coast. And I mean, this needs to be considered. I mean, you cannot, so I mean, this is an entirely different topic, how a society can plan better the land usage, considering the hazards, but also considering the needs of people and some economical development, because if people are poor, you cannot force them to be far away from places where actually the economy can work, right? So it's a complicated issue, and let's see here. So basically the lava flow occurred as soon as it was cooled, and you could actually step on it. They built a new hotel on top of it. And the previous ones was 20 years before, so they actually don't care. If they think in 20 years I will have a new lava flow, fine, I will just build a new hotel. Because everything is lost, of course. Under 20 meters of lava, you cannot recover much. You have generally time to actually take your things out, but the building will need to be completely rebuilt on top of the old one. So the question is more, you know, okay, fine, you want to live there, but are there areas that are at like safer and areas that are a very high probability to be inundated again? So can you actually do this and maybe help the people to choose better where to put infrastructure? So this was actually the aim of this student that worked in my department. She used the lava flow models, and she used in particular the type that doesn't take into account the full physics of the flow, but only the steepest slope, plus some statistical tricks to actually move around a little bit and jump over small obstacles. And so she so this, first of all, is the data, you know. So here, what you can do, what they did, the students, they just, as soon as they heard that there was an eruption occurring, you go there with an instrument. It's called like a, I think, here the difference map, it means elevation data, but it's like a handheld laser-based instrument. I can't remember how it's called, like LiDAR, something like that. You just go to an elevated area, maybe 2 or 3 areas, and the instrument scans the topography and creates a clouds of points, and then you go to another area, you do the same, because some locations are covered by small topographies. So you need to go to several areas to actually be able to scan all the topography. You move around, you have to actually climb a lot and carry the instrument, and then once you are at home or in the field, if you can develop a topographic model. Then you wait, and either from satellite, you can actually do the same from satellite, but it's easier from the field, or you get better data from the field. And then you go in the end, after the lava flow, and from the difference, you figure out where the lava flow actually was. And this is what she did here. So this is the vent, here is like this Pico de Fogo, and this was the lava flow. And then you can simulate so this would be short term, actually. I told you long term is you need to have a probability for everything, but then short term, everything collapses, right? You have just one vent, because this is what, or maybe 2, sometimes there's more than one vent, and then you can run your flow model actually short term, really to tell people this area will be inundated, this area will be inundated, because it takes time anyway for this inundation. And so you can actually help the authorities to manage an evacuation. And then if you do this, so she got, I think, with different assumptions, number of times. Okay, so basically you can get different curves in your model to say number, like here in this case is number of times that every pixel was inundated by a model, because you have to run many, to have a better statistics. And then maybe this is also correlated with the final thickness, is actually more complicated, there are issues. But then you can compare the model, actually the model is this color, right? And here is the comparison with the lava flow. The yellow one, I think it's early lava flow, so basically measured on a particular day, and then the red one was the final lava flow. And the model was this other color thing. So you can see there are differences, like for example, she modeled this area all to be inundated, but actually it was not. Also here, some part, and there, so the upper part is tricky, because you don't know when it's going to stop. So some parts are impossible to guess, some other parts are really like, let's say, what are the limits? Because actually topography evolves during the flow. So the flow also changes topography. And this is not really very well understood. So like after a few days, then you develop a cone, for example, during the eruption, you develop a cone, and you may develop a channelize things, and you may develop, for example, even just a cone will protect the flow to one area, and everything will go preferentially to one area. So these are the differences that are there, and future development, I think, will cover these issues on how better to forecast this. But anyway, I think it's not so bad, because it predicted, like, except for this, it predicted that the most inundation would occur in this area, which is actually what occurred. And it was critically important because some of the towns were actually here. So this one was for the actual vent, okay, like short term, from the actual vent that actually opened. This one is for long term, like if you don't know where the vent is going to be, then what she did, she took like the previous vents, she developed like a density map, like previously we saw for Etna, and then she ran a model for every one of these vents, and then she she got this map. And also for this map, which is a long-term map, here was this hotel that we saw. Here are like towns. It is seen, I think the difference between these two, if I remember well, is this one was with the topography before this lava flow. You know, like as you would have done if you had done a lava flow, long-term lava flow model before that eruption, that would have been the result. And this one is now, after that the lava flow has actually occurred, and how can I say, the interesting or worrying thing is that actually the areas where the towns are still very high probability of invasion. So it's not that even the 20 meters that were added by the lava flow have not changed so much the probability in those areas. So it's still the areas where most flow will probably occur in the future. So you can see that it is actually very important models because they can help. So in this case, it's also important that when you do the work, you write down summary in terms easy to understand for people, and you translate it in the local language, which is, in this case was Portuguese, because then people are able to actually read and make their own decisions. Because in some countries you have people following very much what authorities say, but in other countries there is no such a thing, and people need to know directly in order to make their own decisions. In general, it's good if they can make their own decisions. Like here is just another case of likelihood, which is the colors, and the observation, which is the curve for a lava flow at Etna. Like this was actually what the flow was like. And this was, once it had started, how the model would have predicted it. I think now this is relatively, I can't remember the date, but it's not very new. But these models are improving and are getting better. Okay, this one is hold. This is the same thing for Kilauea. This was before the last eruption. So in this, in the map to the right, we see the lava flows erupted since 1800. They are also, as before, you need to have very good maps. And you can see that actually most of the flows are from this volcano Kilauea on this rift, and this other volcano Mauna Loa. Look at this one that opened on the flank and reached until here, but otherwise on the rifts, and they even reached Hilo, which is the biggest town. And here, actually here the slope is gentle because it's a shield volcano, but not that gentle, and the flows may be very fast, so it's actually very dangerous. And you can actually see that the main road is a road that goes all around the island, and these flows are able to cut this road. And then this is also difficult because you don't have an alternative road. I mean, if you want from here to go, okay, then you have this one road and these other roads, but it's a tricky thing if the roads are interrupted, so you need to plan a lot. And then also here smaller flows. And then again here the inundation probability was just, you see how coarse it is, like areas, okay, I actually don't know, so people, so they just divided the islands in areas where 9, 8 and 7 is very low probability, maybe 7 a bit higher than there because this is really an extinct volcano. While Mauna Kea, I think, is still considered active, so it has not erupted since a lot of time, so people don't think it will, but still it's higher here on top rather than there. Then this one also has very few eruptions and very years ago. Then Mauna Loa high, the rift very high, the rift of Kilauea very high, and the last eruption has actually occurred here, in this area here. So it has, actually it was very well predicted, if I can say. Still, there were many houses in that area. This map of Vesuvius I put because it shows that the topography of the volcano is actually very important in assessing the probability of inundation. Many volcanoes have such scars that are due to previous collapses, you see here. Vesuvius has this scar here, which is partly due to the Pompeii eruption, but also partly due to a previous collapse that occurred before and has created like a collapse scar. And one can see that all the villages, it's at least forecasted, that all the towns and villages that are in the north are actually at very low risk, while the risk is much higher on all these sides. And due to how really the topography is done, then you have high probability or lower probability also for the distance. The last eruption, I think in 1944, had a lava flow, but now I can't remember where actually it was. It had a lava flow that created a lot of problems. Okay, we will look a little bit at explosive volcanism and how you can actually model, especially in terms of conduit flow before actually the eruption starts. So of course this is like an analogy that is more maybe for kids, but nevertheless you have bubbles nucleating and growing, and then you have fragmentation. Just to remind you, is this transition where you go from a fluid containing a gas phase to a gas phase containing pockets of fluid. And the same you have actually more or less in a volcano, where you have a reservoir for the magma, vesiculation. And then at some point, if the conditions allow, you may have a fragmentation. And then from that level up, you will have a gas particle dispersion. So it's basically particles within a gas mass. And then the column, eruptive column. Okay, this is just to show how the plumes are more or less looking like. They have an umbrella region where you have this spreading of the volcanic column to the outside, a region that is called like convective because you have a lot of flows that are due to convection, and then the jet region, which is where the mass is escaping from the conduit. But okay, so what about the magnitude? The magnitude of eruptions is a tricky point. Like, it's tricky for earthquakes, but for different reasons it is tricky for volcanoes, because magnitudes of eruptions, you can consider different parameters to say how the eruption will be big. So one element is how much magma is actually erupted, but this is one possible description, because another possible description is explosivity. So they are two different things, and they are not necessarily, they don't go together necessarily. So generally you have volumes and then the height of the eruptive column. They describe actually two different processes. So some people don't agree very much on the magnitude of individual eruptions, for example, but anyway, this volcanic explosivity index, which is this widely used measure, was published in 1992 and basically describes things in this way. So where you have small eruptions and 100 meter of eruptive column height. And then you go up and up in terms of volume, more or less. And then the columns also go from here to 1 kilometer, 5 kilometers, 15, 25, larger than 25. And I think here we don't know because they have not been really measured. Because so these very big eruptions we have not really witnessed, luckily. Magnitude 8, the last one I think was Toba, 74,000 years ago. And 7, there were others, 7 more recently, but I think the largest, okay, here there is like a comparison. Okay, the big one here, Wawa Springs, it says 30 million years ago, so this is something we hope we don't have to experience. Yellowstone was VI8, and it was like 640,000 years ago, and it had 1,000 cubic kilometers. And then, okay, Crater Lake was like 7,600 years ago, Long Valley Caldera, these are very large eruptions. This is Toba, as I told you, the last VEI8 that occurred on Earth. This one is a relatively recent one, 20 cubic kilometers in Krakatau, 1883. And then here you see other very destructive eruptions that are actually quite small in comparison, like Mount St. Helens in 1980 was just a 4, even if it has a huge explosion. The Vesuvius Pompeii eruption in 79, maybe VI5. And then you have other volcanoes here. So like you see, the Eyjafjallajökull eruption was this that created all the chaos with the airplanes. Was actually relatively small. Pinatubo was a big one in 1991. So this is just a figure to show in terms of mass how they compare. Okay, if you want to study the statistics of these eruptions like you do for earthquakes, for example, again, you have a problem of completeness to study the statistics, because of course, there are areas of the world that are more remote and people don't know very much of those areas, and there are previous eruptions, and so it is actually not known whether, you know, here it goes, the years goes back in time. Here is like the percentage of missing events. So we see that, let's say, the percentage of missing events is very high for small eruptions back in time, clearly. So you know, it's like a graph that describes basically the big eruptions, even if they are back in time, I have a quite high probability that I know of them. But if it is a small eruption back in time, then I have a worse probability to know. So this problem of completeness, of course you don't have necessarily good historical records all the way, but also what people used to do is to go to the geology to see the geology, and sometimes you don't see it from the geological record, and there can be many reasons. So some reason it's really like erosion takes it away and you don't see it anymore, or it's covered by other layers and it's hard to know, or they are there and you don't see them, because this is also, it can be. So how can the tephra, even if tephra is this, you know, explosive material that is deposited on the ground, reasons are erosion, as I said, burial by other younger deposits, or the volcano just completely disappears because you just erase the volcano by these mechanisms. Okay, basically there were 2 times, so this paper shows that there were 2 times, one was 1600 and one was 1900, where the record changed significantly. Like in around the 1600, you know, there was a widespread colonization, which meant that actually the records became a bit better. And in 1900 you had the telecommunication methods that meant also that records became far better. So there are like historical times when that you can really use to actually divide catalogs, because they are good times, because you really see a big change. This would be like a magnitude frequency eruption, like a Gutenberg Richter for volcanoes, and you see more or less it's a power law. Data are not as many as for earthquakes, so we cannot really know for sure, but it looks like a power law. Like for earthquakes, you have very few big eruptions, luckily, and there's many more of them. And this is considered as eruptions per volcano per 100 years. So, and this is the volcanic explosivity index. And here, different from earthquakes, there is like an attempt to link the size of an eruption to actually the state of the volcano. First of all, what volcano it is? Is it a caldera, or is it like a different type? Because different types are linked to different potential. Let's say large eruptions only occur at calderas, for example. But also the state of the volcanoes. Like if you, so basically if this really worked, maybe, then you could actually, from the satellite, look at the volcano in a remote area that you don't know, and figure out what is the frequency of that particular, what is the statistics of that particular volcano. Like here it says that basically distributed cones and fields, they actually map more here in this area, where you have smaller eruptions basically from those distributed cones and fields. So this is like monogenetic type. Then there are open vent stratocones, semi-plugged, and well-plugged. So this is like an attempt to link the eruptive potential from the state of the volcano. So open conduit means basically that you have continuous degassing from that volcano. So gas is released efficiently and you don't store it in the magma chamber, and therefore you are basically lowering very much the probability of an explosive eruption. And then, but then you can have semi-plugged or well-plugged. Then well-plugged would be Vesuvius now, for example. There is no evidence for a very much degassing. Like Etna is considered open vent, because always you hear explosions. Stromboli would be open vent. You know, you hear explosions, you visit, and there is degassing. Eruptions are occurring very often. But then a volcano can become semi-plugged or well-plugged, and then you have large calderas. But even if you make this distinction, they all plot onto kind of a power law for volcanic explosivity. So let's have a look a little bit at how, what people think are behind Strombolian or Hawaiian activity. It is about these are efficient degassing styles where gas can escape very easily from the magma chamber, and we will see a movie that has a slug flow and annular flow, which is here. Basically, these are low viscosity regimes. You cannot have this in very high viscosity magmas, because you have the viscosity of the magma needs to allow for the bubbles to move, to ascend. So there is this movie. It has some music, but I thought it was the best movie I could find. So we will hear the music. shows the transition from a bubbly flow to, so basically with time you see the flow rate of gas increasing, and then you will see how the regime changes in the flow. This is actually very much well known because it's used also for pipes in engineering. Everything which is used in engineering is well known. Greek music. Because it shows a lot of things in short time. It's entertaining. So basically, you see that it depends on basically two factors. One is the flow rate. Where was this slide? Here. Yeah, one more. So here you see, depending on how much gas is released, then you can have different flows. So these are pretty obvious, I think. Maybe these ones are a bit less obvious. So here you can start to see that the bubble coalesce very much, and then they form these slugs. They are called slugs. And then here you have this churn flow where you have like a mixture, a transition between this kind of type, this type, and this type. Here is just one long annular flow. Means basically you have a ring of liquid on the wall, but in the middle you have just a continuous gas flow. So it is thought that these bubbles here, like these regimes here, they are just when you see some degassing, like continuous degassing, while this is linked to strombolian eruptions, which is like you have to wait 1 or 2 minutes, for example, or 6 minutes, and then you have an explosion. You have to wait again, and then you have an explosion. So basically there are these gas slugs that reach the surface, and when they reach the surface, they expand very fast and explode. While this and this, they are more related to lava fountains. Like you have a continuous supply of gas and fluid, and the gas helps expanding, and basically it carries the fluid in this way. So I wanted to show you very quickly a strombolian eruption. this really stromboli, so the cool aspect of Stromboli, if you ever have a chance of visiting, I went to Stromboli, but I couldn't visit the summit because it was closed when I visited. I think now it's open, you have to go with the guides, is that the summit is actually higher than the current vent where all the eruptions occur, and you can sit on the summit and overlook the explosive vents. So you see how it is, you have to wait. And then you see something like this. Yeah, so it is thought that every time you have one of these explosions, it's because one of those slugs ascending the conduit. Actually, no, this is yesterday. Where is it? Actually, all these models are generally for cylindrical pipes, and this is a little bit of a limit because actually this is a simplification, let's say. Sometimes you do have cylindrical pipes in volcanoes, but for example, Stromboli has they say the dike-like conduit. It's like a thinner, elongated thing, but in principle it is the same thing. So I found in a presentation by Michael Manga this map, which I think helps a little bit understanding all the regimes. So here is the logarithm of viscosity. Here is the mass discharge rate. So like depending on the velocity of the flow in the conduit, which actually is a function again of how quickly gas expands, because the mass discharge is not really how quickly gas sorry, I did some confusion. How quickly magma is ascending from the magma chamber, and then on top of it you also have the gas bubble formation and bubble growth. So of course, if you have viscosity law, here you are in the basaltic regime, here. Then you have strombolian or effusive, and then here you have Hawaiian, which is basically lava fountain. And here is like a regime, he writes inertial fragmentation. What is inertial fragmentation? This fragmentation is not occurring because you have because bubbles, so we talked about that bubbles may be limited in their expansion by the viscosity of the fluid. Here is not the case because viscosity of the fluid is low. And so why do we have fragmentation if this is not the case? It's called inertial when basically anyway bubbles are expanding so much by rising in the conduit and due to the compression that basically they break the magma by their own expansion. So without having any, so that the strain rate becomes so big by the expansion that basically everything becomes gas. And it is just driven by inertia, by the flow velocity, this expansion and fragmentation. And this is what creates lava fountains. While if you have higher viscous magmas, so here you are in silicic and crystal-rich magmas, then depending on how much mass discharge rate, you have effusive domes or coulées. This we saw at the beginning that you create a dome And you can have permeable outgassing. So you are actually repressing explosive eruptions because the conduits and domes are permeable, so all the bubbles are joined and linked, and gases can escape easily as the magma is not moving, but they create networks, and then you still have efficient degassing. So you have an effusive dome, effusive eruptions, even if the magma is very actually dense, very viscous. While if you are in this other regime, then you have a very high flow rate. The rate of expansion of bubbles is very high. They don't have time to link each other into a permeable outgassing network, and they are limited in their expansion by the viscosity of the fluid, and then here you have very explosive eruptions. So this is just, and here you can see that it is like ascent velocity in meters per second. So you have really, I think it's a good diagram to have an idea why you have all these eruptive styles, and that they mainly depend on the viscosity and the velocity of ascent, which of course also depends on a lot of other parameters. So how are these flows? So how do we get a velocity of ascent, for example, and other, so we need to create a physical model for the flows in these conduits, and these models are complicated in the sense that you need to put in there a lot of interacting factors. You need to put a model for magma viscosity as a function of temperature and composition. This is critical. A model to show for the solubility of gases, so how much gas will come out at a given pressure and temperature. For the diffusivity, because the gases also, we talked about that, they diffuse from the molecules into the bubbles. Then you need to have a model for bubble growth, so you need to take into account surface tension and bubble growth, also due to the compression. You put a criteria for fragmentation, which is where do you think the transition of regimes occur. And these models are full of parameters, and you need to fix them by using theory or experiments. So about heat capacity, surface tension, the strength of the bubbles, and how much pressure do you need into the gas to actually break the bubble walls. And then you have boundary initial conditions, the melt composition, the temperature, pressure, conduit geometry, which is critical, and also wall rock properties. So you see these models are very complicated, and they are, I mean, they are used very much for simulations, and they actually reproduce a lot of what is observed. I don't think they are really very much used really to forecast in detail, because you don't know, so the uncertainties in the parameters is so big that actually you cannot, it's very hard to really use them to reproduce something that you want to use for a forecast. But they work really well, they are very well established, and a lot of work is put into solving some of the details, you know. So anyway, how are they really built? You need to put, so the main laws always are the conservation of mass, conservation of momentum, and energy. So basically, conservation of mass is translated into the different phases. You have a gas phase, you have a fluid phase, you have crystals, and at every height in the conduit you have to have the mass flux that is consistent in itself. Then you have momentum and energy, and then you, of course, you need to have viscous dissipation of energy, change in density, and then you have also rheology for the different models. And then there are a lot of assumptions to simplify actually the equations. One, that we don't have any turbulences, that everything is relatively laminar, actually not necessarily laminar, but not turbulent. And then you can put fragmentation, and so you put yourself into like a more of a effusive flow. And a lot of these models have cylindrical conduit. There is an attempt to actually consider elliptical conduits, and this afternoon I will explain you better why this is important and why it's becoming more and more done to have actually to relax this hypothesis of cylinders. You treat the magma into individual phases. You have to have also the exchange between the phases. Some mass will go from one phase to the next. So a lot of equations you can imagine. And then there may be other hypotheses and so on. So again, mass conservation for the liquid and the gas phase. Momentum equations in there where you put the gravity forces, the conduit resistance, inertia, and so on. And then you have transfers of momentum between the different phases, and energy and dissipation of energy by viscous forces. And then we saw also before bubble growth, all the physical properties, the fragmentation, and boundary conditions. These are the main ingredients. And then there are different models done by different groups. And then I will show you now a little bit what are the most recent advancements, like these codes. Before they were 1D, then became 2D, then became 3D, but they were already established maybe 20 years ago, like the main equations were kind of known. But then people noticed that they were not really predictive. And so, like, for example, this is a Stanford group where they started to develop I think a very important advancement, at least in principle. Now I'm not sure whether it's already, very, very high forecasting power, but the principle is that you have to balance the physics well. So a lot of these, there are several elements. One element is all these conduit flows, the initial, the traditional models had the input from below was very simplified. Like you had, for example, a constant mass flow from below, from the magma chamber, at the same initial conditions. So the pressure maybe either, so the pressure was maintained constant, temperature was constant, and then everything was starting from there. However, if we look really at the data of an eruption, and we will see some of them also this afternoon, actually what I see is that the eruptive rate, very frequently, you see that eruptive rate, this is also true for effusive eruptions, but also explosive eruption, both. Eruptive rates initially grows, and then it goes something like this, You have, but this cannot be predicted with these models where you have pressure and temperature always the same at the bottom, clearly. You will not achieve an evolution of the eruption. So people have started to think, okay, but how can I then reproduce really my observation of the evolution, not only of the actual, steady state. And then there are several factors that people have started to include. And here one is very prominent, you see it very, very easily, is the coupling with the magma chamber. Like if you have a magma chamber, we have mentioned this already many times, if you have a magma chamber that fits an eruption, regardless of whether it's a dike or whether it's like a conduit or so, this reservoir is coupled with the flow. So as soon as you drain it, pressure will decrease. And so basically it needs just to be very simple equation saying mass conservation works also for the magma chamber. And if I put this, already I am going into this direction. Actually not very much this yet, but I get, this is the main point, I get the exponentially decreasing flow rate because the magma chamber loses pressure. What about this first part here? This was recognized earlier on, that you have a phenomenon called erosion of the conduit. So basically you start with a given conduit, actually initially probably you start with a kind of a dike, and then you erode the walls of the dike, mainly actually in this way, and you create, and this is seen in observations, because if you go to the field and you look at the eruptive products, you see that they contain what is called like lithic fragments. It means fragments of the rock, fragments of the conduit wall. They are there, and actually you can even assess how much. You can study how much fragments were included in what phase of the eruption, you know, because you can go to the field and see first deposit, second deposit, third deposit, and then you can measure it. And this is starting to be included, and it's very important because this is what actually creates this phase. Because if you basically enlarge the conduit and you change the geometry of the conduit, you make it more larger, then you have an increased flow. But then if you add also coupling with the magma chamber, you know, and in the early phase, magma chamber is still very pressurized, and so what you have is you increase the flow rate. But then at some point the magma chamber is drained enough for this choking to control the flow rate, and then you get a decrease and you go this way. Then of course this is also simplified model, because generally you have like it goes, then you have again, and then you have again. You may have several phases. Some are really like this, like entirely like this. Some are more complicated. One reason can be that you tap different chambers at different time. We know that the plumbing system is actually kind of layered. So as soon as you finish one, you remember this slide that I showed you with the layers at different depths. Once you finish one, then pressure gradient is enough, and you start to get a flow from the bottom to the top. And then you have a new eruptive phase, and they all go basically in this way. So this is what may happen. Okay, so you have coupling with the magma chamber, erosion in the conduit, and then there is the very main part here is to use actually data. You can be surprised, but data were not really used, geophysical data, very much in these flows to constrain the properties of the flow. So how the philosophy of this particular series of papers by this group is that they are using GPS and tilt data of deformation to recover the conditions and the unknowns in the numerical models. So how does it work? Basically, it works in a Monte Carlo way. So basically, you start with every parameter. You have a big list. Every parameter with a range of reasonable range of values. They are, you know, and then you start to shoot then Monte Carlo, like take a random set of parameters for the initial conditions. You run the model and you calculate from the pressure. Actually, generally in geodesy you have just a pressurized conduit. Here you have also tractions due to friction, so you have to be more careful about how you calculate actually the deformation. It's not so much only pressurization of a magmatic source or of a dike, but you also have a viscous flow, and the viscous flow is also creating deformation. Anyway, you calculate everything, and then you calculate your data at the surface. And you do that for many, many models. You do that for a lot of combinations of the parameters in a Monte Carlo kind of thing. You can use Monte Carlo Markov chain is a way to actually compare immediately. So it's a better algorithm that allows you to converge in your Monte Carlo simulations by comparing early on with observations. So basically what you do, is my solution close to what I actually observe? Yes, then I shoot my parameters closer to the parameters that I had, and only rarely I jump one parameter a bit farther away just to explore more parameter space, you know. Then again, I run my model. How close is that? Is it closer than the previous one? Then I go and look closer again to this parameter space. Is it very different? Then then I look in some other parameter space. In this way, by using this algorithm, you are able to basically create probability distributions for each parameter to reproduce actually the observations. Is this clear? Do you have a question? So basically it's a way to model data without really, for considering processes that are very complicated. Like this is highly nonlinear, you can imagine, you know, all these equations and then, you know, compressible flow and everything is highly nonlinear. Therefore, it's difficult to reproduce data in like a calculated way, I don't know how to say. So basically you do it by chance, you know, you shoot a lot of the parameters as you are, and then when you actually hit a good solution, you go back and you try to explore those parts. And you do that in a controlled way, and then in the end you reach, okay, I found that I have like two minima meaning like the misfit between my data and my solutions, and I have two regimes where I can reproduce those data. One is with this particular combination, one is this other particular combination. And then in this way you learn a lot. You learn about the parameters of your system. And I think this is very important in general as an approach, and that I think it's a very big innovation, and it will be used more and more. I think it is in general used more and more to couple more advanced statistical methods to physical methods to get a better idea of a system, like for forecasting. So basically this goes into a bit more philosophy, but I think it's important. Like if you use deterministic models, physical models, they are elegant, beautiful. However, unless the physics is really kind of simple, for example, you know, ballistic and projectiles and this, you know, they work super well because the physics is easy. It's hard to actually predict, and the reason is that I don't know very well my parameters. In complicated systems, even more so. The reason is not so much that I don't know the physics I know, but I don't know the parameters. And then if I think I know the physics well, but I don't know all the parameters because they are too many, or I cannot observe them, they are just conditions in the inner of a volcano that I will never be able to observe, then, you know, okay. Then I have a different method. A different method would be just statistics. You know, I look like before the lava flows. I only look at where a previous flow has been. This is fine if you have many data. You can go completely data-driven if you have many data. You can forget about the physics because the physics will be sampled. From the process will sample the physics, and if you have enough realizations of this physics, then your result space will be dense enough that you can actually make predictions only based on that. And these are like data-driven approaches today. A good system is to combine. And then this method is like a combination where you have a statistical method that basically helps you getting the most from your actual data. So you have a complicated physical model where you have some unknowns, which are actually the parameters or the initial conditions, whatever, and then you use advanced statistical methods to constrain what you actually are missing. And then once you have done that, then you can do the forecast, because you can use the probability distributions for these unknowns and run many models, and then you have a good forecast. You know, so it's like combining physics and statistics to have a forecast. If you, okay, we can talk about another aspect is forecasting power with respect to explanation power. So if you, maybe I will talk about this later, because it's also another important point. Do you have questions? So just to summarize, current models of conduit flow, I think the most advanced are considering modifications in the, so basically are trying to relax hypotheses that were done in the past to simplify the models in order for them to be solvable. Of course, at the beginning you need to cut down, and make the problem solvable, then you have a solution. Once you have it, you need to start to consider your hypotheses and see how you can relax them and how you can develop more complex models that address complexities in observations that otherwise cannot be explained. So it needs to be necessary because the data are there, and in the data you see something that you cannot model with your existing model. Then you need to complicate it. Okay, so how in case of conduit flow models, some effort is dedicated to actually going into the details of the equation and get a better momentum transfer between gas and crystals, better, all these like micro processes, but also to include an overall balance in the volcano. So include coupling to a magma chamber, including erosion of the conduit in the different phases of an eruption, including data. Here is the formation data, but in theory you can actually include better, you can include even these lithic fragments data. You can do the same with the lithic fragments. I've seen a paper doing actually exactly this. So basically they went to the field and they measured how many of these lithic fragments were in the different phases of an eruption of Vesuvius. And then they did a very similar thing. It was very coarse and not Monte Carlo, but like, okay, we put 10%, 20%, 30%, like a very coarse grid search. What if I put this number, then what is my model returning for me? Okay, it returns that I should have an eruptive column as high as this, which is consistent with the data or not, Okay, if I find that for 10 is too little, 20 is too little, I need at least 30% to actually reach a result in my modeling that is consistent with what I observed in the deposits, and then you figure out, so you can actually use geology, you can use physics, you can use a lot of things it's like an inversion approach, right? It's an inverting for some of the unknowns by simulations, by doing simulations.
So what is a eruptive column? Eruptive column is the projectile?
Eruptive column height is really how high the jet reaches, yeah, so up to the top. And this is a measure of course, of the energy that is and velocity of the jet. Yes, and then it's not only projectiles because it becomes like really ash, and then ash has if it's very fine, it's transported so you have water vapor and other gases with a very high temperature, and you have these convections. And the ash is light, and then it gets ionized. So actually, projectiles are bigger bodies that really don't care so much about the convections, and they just go ballistic. You have this that just go ballistic, and then you have a lot of finer particles that are up in the plume, and they get transported to very high elevation until the jet has a high enough speed, and then if the jet loses speed, then everything falls down and collapses, and you have the pyroclastic flow. And also this is so you see that actually the model, the coupling to a magma chamber and the loss of pressure is very important to actually model the time when the eruptive column will collapse, because you can see this phenomenon that the plume is not sustained anymore, collapses, and then you have a different flow down the flanks. Okay. For now,